afternoon, everyone. Thank you for staying around. So I'm James Hopgood, and I'm a lecturer from the Institute for Digital Communications in the School of Engineering, just in case there's someone here who's not from engineering. So today I'm going to talk about some work I've been doing over the past year, which has been an industrial secondment with a company in Edinburgh. I'm going to try and avoid naming names, just because this is going to go on YouTube. But it was an interesting little signal processing problem, and I'll discuss what signal processing is in a while. It's an interesting little problem which they approached the university about, and we've had some good success with. So this is a very sort of small, specific piece of research, but I hope it's interesting. But to start off with, I'm going to talk about what signal processing is, and generally what the kind of research that I do. So signal processing is part of electrical engineering, although it's probably even broader than that. And it's a discipline which tries to extract meaning from the measurements that we take around us and to try and sort of infer some benefit. So to describe that in more detail, imagine that we've got a scene that we're trying to observe. So my area is audio and visual signal processing, so I'm observing it with cameras and microphones, but it doesn't have to be. That scene could be anything, so it could be the internal combustion engine that we've just been talking about, or Javin was talking about tomography for looking inside objects that you can't normally see. So the scene doesn't have to be something that we can see with our own senses, it could be something else. But we do observe that scene with sensors. So we have microphones, we've got a CMOS camera, and out of those sensors comes a signal. Now the key thing about a sensor is that you can never get to exactly where you want to take the measurement. A sensor is always distant from the thing that you're trying to observe. So therefore the signal that you've got out of that sensor is probably distorted. It's either got background noise or it's just being corrupted by the system it's travelled through. And therefore, in order to extract meaning from that signal, you're going to have to process it in some way. So I'm not going to go into the details of all the kind of processing that you can do, but we have heard quite a few processing aspects this afternoon. So we put that through an algorithm. So an algorithm, okay, it's encoded up using a bit of code, using C++ or MATLAB or whatever, but that algorithm is going to manipulate that list of numbers, which is the signal. And after you've manipulated it, you can probably come up with, let's get that to play. You can, okay, we abandon that. You can come up, this would have been, it shows sort of tracking, this diagram would show tracking a person as they move around the room. So the particular application would be, if you're doing this video conference scenario where you're trying to record me, if I started moving across the room, this camera could adjust and point in the direction where I actually am, just by either observing the image or perhaps even just taking measurements from the direction that the sound is coming from. And at the end of it, you've made some high-level inference, for example, where people are, what they are doing, and what they're saying. Now, what got me into signal processing, sort of almost 20 years ago when I did my PhD, was digital audio. Now, this slide sort of seems a bit out of place, but it will actually have a bit of meaning in a while. So 20 years ago, digital audio was on CDs, and CD players were actually very fascinating devices. So I imagine the students are probably looking at this thinking, what on earth is that big black brick, whilst the older people I can see here who are nodding are going, yeah, I've got one of those in the garage and I'd love to get it out. But this is an amazing piece of engineering because it covers a number of different disciplines. Built into this device, you've got electronic design, you've got control theory. So the control theory is because the CD doesn't spin on an exact point. So it's actually going to be sort of spinning slightly off-center, and in order to sort of track that sort of off-center spin, you'll need some control theory to adjust for that. You've got the signal processing to turn the digital stream into an analog stream, and so only my second year students who are here are going to find out how that works pretty much this week. But you've also got the image sensor, so Phil was talking about lasers earlier. Then you've got to observe the reflected laser off a disc, so you've got the imaging sensor. You've got mechanical engineering, and there's going to be some software engineering, so the firmware. I think Javin mentioned FPGAs earlier. So it's a very multidisciplinary area. And one of the things that I liked about these CD changes, especially the free CD changes, is that if you ever watch them, in order to get the most compact size, they actually follow this rouleau polygon, which is a way of drilling out a square hole. So I don't know if you've seen that before, but you'll notice that they don't actually rotate around its centre, it rotates off-centre. So I found these multi-channel, multi-disc CD players absolutely amazing. So for the students, that's all being done away with, and we have a nice smartphone instead, which is still an amazing piece of technology and multidisciplinary, because it's got battery technology, screen technology, and so forth, and a lot of communication technology. But as a true engineer, if it doesn't move, maybe it's not quite as much fun. Now, I did think actually the CD changer was the last true piece of domestic technology that had that mechanical element and the signal processing and the electronics. But there's something someone mentioned earlier, I think it was Adam on robots, that made me realise that's not true. Perhaps these autonomous vacuum cleaners that you put in your home and they just drive around and just clean all day, actually they're probably a good combination of mechanical engineering and electronics and signal processing and everything else as well. Okay, so just for Ricky, there's got a blank slide in. So that's generally my research interest. So what I'm going to do now is to tell you what I've been doing in this secondment for the past year. And it's completely different. It's in life sciences. So when you think of life sciences, what do you think of? Well, the first thing is DNA. So DNA sequencing, in particular, is probably one of the major breakthroughs we're going to have in healthcare. If you can sequence a genome in some way, then you can basically come up with the following advantages. So you've got more precise diagnostics of diseases, earlier diagnosis, you can have faster clinical trials, you can develop new drugs using the information you've got from the sequencing, and you've got treatments and cures. Now, I think it was 10 years ago when they first did the Human Genome Project, that cost about $3 billion to sequence 6 humans. Nowadays, with next generation sequencing technology, you can basically sequence a DNA sample for $1,000, so substantially cheaper. Now that's just, it costs $1,000 every time you push a button. It will probably actually cost more like $40,000 by the time you take into staff costs and the infrastructure and the machines and so forth. So DNA sequencing is now cheap, but it's not that cheap. Okay. So in the genomics lab, there is an alternative. And this is a process which is bread and butter to anyone probably who does biology or biochemistry of some kind, and it's called gel electrophoresis. And this is a technique for analysing the sort of macro level of molecules to see how much content there is in a particular sample. So the way this broadly works, and I do it for DNA, is that you take a DNA sample. So if we have a look at the left-hand column there, you put the sample in at the top of a slab of gel, and DNA is negatively charged. So if you apply an electric field across that DNA sample, it starts to move towards a positive charge, the anode at the bottom. Now, this goes through something called a gel, which is why it's called gel electrophoresis. And that gel is a bit like running through a forest, right? If you're a small person, you can probably run through a forest very quickly because you can dodge the trees and you're just generally smaller. So small particles move very, very quickly. If you're very, very big, you're very, very large, the trees are going to get in the way, so you're probably going to have to zigzag through the forest instead. So that means that very large particles move more slowly. So electrophoresis is it's part of a subject called separation science, which spreads out the molecular weight of that sample basically along this channel. So the small particles, the small fragments at the bottom, the larger fragments at the top. Now this is not full DNA sequencing. On the right here is just a sort of general sort of image taken of that process. So what are the applications of gel electrophoresis? Well, you can either use it as a tool on its own, so you can use it for analysing proteins or RNA. So I was going to put a picture of some lasagna up here, but I didn't, as they were saying in The Apprentice, I didn't really want to upset any large supermarket by naming who they were, but you'll know that there was a bit of an incident a few years ago where your favourite lasagna had horse meat in rather than actual beef, and in order to sort of test these lasagnas, test the meats, they actually used electrophoresis as one approach for doing that, because for proteins you can get basically a fingerprint, essentially DNA kind of fingerprint which is able to uniquely match to a particular protein. Now, it can also be used as quality control for next generation sequencing. So I said that next generation sequencing costs, in the tens of thousands of dollars by the time you take into account the net cost. But before you go and hit that button to do the next generation sequencing, you have to be sure that your sample that you're putting in is not corrupted in some way. Because if you do that and you press the button, that's $20,000 down the drain. So what you'd prefer to do is a simpler process which you can then look at, and it tells you that the sample actually has the quantities in that you're expecting. Electrophoresis is very, very cheap. It's, instead of being tens of thousands of dollars, you're talking about hundreds of dollars. So you're talking about a factor of 100. So that's very important. So it's pretty cheap, relatively speaking. Okay, if it's maybe it's between $100 and $1,000. We're not going to be doing it sort of willy-nilly, but companies would. Okay, so in the genomics lab, it's bread and butter. If you do biochemistry, you'll probably be a PhD student who will be doing this because it's incredibly cheap in the lab. But we are engineers, and so whenever we see a process, we think, let's automate it, because there's no need to do this by hand. So there's a bit of an in-joke here. If anyone, there's a website called Let's Automate for home automation, which I love. But this is a machine from 1998, and there's a slab of gel where you put your sample in, you apply the electric field across it, your sample spreads out, and this basically automatically takes a picture of it. And relating back to the CD player, the fascinating thing about automation is that it has all the disciplines in that I spoke about earlier. So it's got electronic design, it has image sensors, it's got mechanical engineering to basically put a sample in, make the process work, control theory, and so forth. So on the right here is taking an image of what happens as you apply that electric field as you go through time. So it's a big industry. There are several large companies around the world who do automated electrophoresis, and they use varying different techniques. So whilst I've shown you so far an image, in fact it's not really an image, it's a one-dimensional signal. So I've just taken that image and I just sort of span it around. So really your signal looks like this. It's a sequence of peaks, and this separation axis is really the size of a molecule. So small molecules are on the right, large molecules are on the left. The area under each of those peaks tells you information about how much of that particular molecule is there. So that bit of information is important. Now, the separation of those peaks is also important, and it's something related to basically resolution. So I'll give a quick analogy, make sure I don't run out of time by throwing in some ad hoc analogies. But an analogy might be a security camera in your home. If you want to know whether your home is being burgled, you could get away with a very low resolution camera, because you just need to know the difference between what your home normally looks like and what it is when someone unauthorized comes in. So just for knowing whether it's being burgled, you don't need a high resolution camera at all. If you want to identify the person who is burglaring your home, then you need a very high resolution camera, especially when the camera is far away from where the person is. So depending what application or what you're trying to get out of the information you're measuring, resolution is important. So resolution here is basically the distance between the two peaks divided by the sum of the width of the peaks. So high resolution means that the width of the peaks are very narrow. So I've got two diagrams here, and we can see that this lower graph is much more resolved, the peaks are much sharper, and in fact, if you look at the first peak, the top graph, which has low resolution, the peaks are actually merged together, and in fact there are two peaks at the bottom. So resolution is very important. So one of the objectives when you design an automated electrophoresis machine is to try and maximize the resolution as you measure it. So on the right here, we have two possible devices which have measured it in different ways. On the left is low resolution, and on the right is a slightly higher resolution. Okay, so the secondment was about trying to take basically an existing product and make it even better, improve that resolution as much as possible. Now, just if I play this video again, that might be tricky. Okay? What the existing techniques for electrophoresis is what you'll do is you'll apply electric field and you'll run the electrophoresis for a certain amount of time and then you'll stop. You'll take an image and you'll take this data and you'll put it into your data analysis tool. That's it, stop. So the idea that we came up with is why stop? What happens if you actually carry on this process after you've stopped? It's a simple idea. Well, what happens is these peaks carry on spreading out and they get further apart and they carry on getting wider due to diffusion. But the trick is they spread out quicker than they get wider. So that allows us to do a trick. First of all, it allows us to take all the data across time. So we're taking multiple one-dimensional signals and we create a genuine two-dimensional signal. And then we're going to basically try and combine all of those signals together. Okay? So what happens is, as I say, if you run the electrophoresis process for longer, the peaks spread out more. So if you look at the position of these two peaks, they get further apart and they get wider. But what turns out, if you could map this second trace back to the original trace so that they're overlapped as there, what you actually find is you've got better resolution. So what we're going to do is run the process for longer, get more information. We're going to realign all the pulses, and that allows us to extract the best resolution peak from each point in time. Okay, so one question is, why is this process new? Why hasn't it been done before? It seems like a very obvious process, so what's changed? Well, things have changed. As I said, that first electrophoresis product was 98, and since then things have moved on a bit, but things that have improved are better sensors, high resolution cameras, the mechanical control has improved, we've got more CPU power, and the way that this particular approach that I'm working on is just generally unique and allows us to do things that other approaches don't. So this diagram shows the improvement that we get. So basically, I think the key thing from this slide is that if you watch over time this peak on the left, you just get much better resolution. You've got information that you wouldn't have otherwise, and that will allow you to give, if you want to identify a particular molecule, you can do it better with this particular approach. And this is a graphical representation to show how you align these waveforms. This actually knows the right answer. This is trying different realignment estimates, and when it's got the right one, which it will have in a moment, you'll see that all the peaks just sort of overlap. Okay? And finally, then what happens is you can fuse this information together. And so this, by the way, I forgot to talk about the title of my talk. So electrophoresis is part of a discipline called separation sciences. So you're doing electrophoresis to separate out a signal, but the signal processing is going to come in and it's going to fuse all the information back together. So that's what the marriage is. So remember, the title of the talk was Separation and Marriage, Signal Processing for Life Sciences. So if we fuse all that information together, we get, for example, the top graph was the original graph, the bottom graph is the sort of refined one, and you can see that the peaks are much more resolved. And that's a very simple case, it's just a DNA ladder. If I show you more sort of other cases, you can see the benefits. So one of the things about the cross-disciplinary research is that I had to go into this secondment knowing nothing about life science, and now knowing a little bit more, but I'm sure that I'm talking in a way. If we had an expert here, they'd tell me everything you said is not quite right. It's a bit like doing an A-level and going to university and being told that everything you knew at A-level was wrong. It's important that you find the right project, because when they're the right projects, they are fun. And the sort of take-home message is that separation always helps in a variety of engineering problems, but as long as you can fuse or marry the information back together. And my real punchline is probably only about 2 people in the room who know this, so I am getting married in the summer, but I am not intending on getting separated beforehand. So, and just because I went on a 3-hour university course which told you that you had to acknowledge all your plagiarized graphs, because we tell students off for plagiarism, these are all the links, so when this goes online, you can go and click on them and find out more, and there's a second list. Okay, so thanks very much.
This production is brought to you by the University of Edinburgh.